All right, so we're about to look at some problems, but before we do, just wanted a quick reminder about one of the new big formulas that we have, that is that angular acceleration of an object, which is rotating, is equal to the net torque divided by the moment of inertia. And this is an important formula because what it sort of shows that angular acceleration is the result of these other two things. These two things come first, so to speak. In other words, you can apply a torque by putting a force on an object, or multiple forces at different locations, but yet you can actually add all those torques up, and whatever the net result is, that's going to cause rotation, but it is going to be affected by the moment of inertia, which is where how much mass the object has that you're trying to rotate, and where that mass is located. So just sort of visually what that looks like. So the moment of inertia, as we mentioned earlier, it's the rotational equivalent of mass. So you can imagine if you have maybe some people on a merry-go-round, and the mass of these other three students are on the edge. It's going to be harder to get this thing rotating because they're all the way on the outside of the edge. Meanwhile, if they're in the middle, they're all really close to the pivot point, then the moment of inertia is smaller. It's going to actually be easier to get it rotating. So to summarize, an object's moment of inertia depends not only on its mass, if there's a few kids or a lot of kids, but also how that mass is distributed around the rotational axis. All right. So we talked briefly in class about the connection between and the similarities between linear dynamics and rotational dynamics, where you've got net forces, mass, and accelerations. Linear acceleration, that is. In rotational dynamics, you have rotational force, which we call torque, the rotational impetus to get the thing spinning, moment of inertia, and then angular acceleration. And Newton's second law, acceleration is equal to a net force divided by the mass. Before anything can get accelerated, you've got to have a force on it, but that is going to be affected by the mass, which both of those in conjunction together will determine the acceleration. And the same thing rotationally speaking. You have a torque or a bunch of torques working together, and then that's going to be affected by the moment of inertia of the object. And some great mathematicians and physicists working together have actually figured out the moment of inertia for many common shapes. And this table is in your book. It's table 7.1. And there's some basic shapes like a thin rod, or a plane, or a slab, or cylinder, or disc, or a hoop, or maybe a sphere. And these are sort of basic shapes, and they have gone to the trouble of actually figuring out what is the moment of inertia if the axis of rotation is at these different locations. So for instance, for a thin rod, if you're rotating it about a line in the center, then the moment of inertia is 1/2 mass times its length squared. You say, how in the world did they figure out? Well, assuming that this rod is uniformly distributed, all the mass is evenly spaced, they actually can add up all those different particles and figure out how they're all going to affect the rotation. And so if you say, how in the world could they add up all those different infinite number of particles? Well, calculus will get you that. And it turns out to have these really nice formulas. Now notice it's different. The moment of inertia is different for a thin rod rotating about its center than it is at the end. It's 1/12 ml squared versus 1/3 ml squared, and 1/12 is a lot smaller. You can figure this out if you had maybe a meter stick and try to rotate it in the middle. If you had to put your hand at the middle and try to spin it back and forth, versus if you put your hand on the end and try to move it back and forth, you'll find out that it has a lot more inertia here. And then you can see other objects. The cylinder or disc, 1/2 mr squared, we're going to use that formula quite a lot. And you can see if you have the same object or same mass, same radius, but in the form of a cylindrical hoop, then the moment of inertia is mr squared, which is double. So actually, something that has all the mass distributed around the edge, it's harder to get it going. It's hard to get it spinning, so to speak. But it also, once you do get it going, then it will tend to stay in motion, tend to keep rotating. And the same thing with spheres if you've got a solid sphere versus a cylindrical sphere. This formula is also there again presented at the end of the book. So um, when we're using Newton's second law for rotation, there's some strategies that we can use. We're always going to model the object as a simple shape. In fact, all of the homework problems and the problems we're going to see here in a minute are all based on these shapes right here, the disc or the hoop or a thin rod. So we identify where the object, the axis around which it rotates. We're going to identify all the forces, calculate all those torques, and then basically use one variation of this formula, this Newton's second law, alpha equals net torque over moment of inertia, or multiply both sides by a moment of inertia and you get this net torque is equal to I alpha. And then, so we'll use that formula to sort of link a lot of different things together and then use our rotational kinematic formulas that we talked about earlier in the chapter, such as omega equals omega naught plus alpha t and all those other equivalents. So let's get started on some problems here.